Our next speaker, well, there's two speakers actually. Bing Zhu, who's going to be doing the talk, and Mark Zwolinski, both from University of Southampton. Mark's the professor and Bing is the PhD student. Investigating the vulnerability of processor cores to single event upsets. And Mark's research interests include microelectronics reliability, design for test, and simulation. Okay.
So Bing will be doing the talk. I'm just here to field off any nasty questions from the audience.
It's his first talk, so be gentle.
Okay, so hello everyone. My name is Bing Xue, and my supervisor is Professor Mark Zwolinski. Today, we want to present our recent research about evaluating hardware reliability in the presence of soft errors. So I will divide my presentation into the following parts. So the first part will be our research motivation, and the second part will be our proposed method. In the third part, I will explain our results, and the final part will be the conclusion. So let's move to the first part. We choose single unit upset as our fault model. Single unit upset has been a major concern in embedded systems. When an energetic particle, mainly an alpha particle or a neutron particle, striking a sequential element, causing a bit flip, a single unit upset occurs. A single unit upset may also occur if a single unit transition, which is caused by an energetic particle striking a combination logic, is latched into a sequential element. Some single unit upset may cause something, others may cause nothing. So the traditional way to evaluate single unit upset is a simulation-based fault injection. The basic idea of a simulation-based fault injection is to inject fault, running a simulation and monitoring the response. So as shown in this picture, a blue circle represents a state. Different color of lines represent different paths. So in each simulation, at most one fault is tested. To test multiple faults and to cover all the state space, multiple simulations are required. However, it is impossible to test all faults due to time limit. So most researchers choose to use random fault injection, which leads to limited fault coverage. In addition, a simulation-based fault injection is a fault tracing approach. It is quite hard to use a simulation-based approach to find a candidate fault for a given failure. So can we solve these problems? We choose RISC-V IBEX core as our test platform. RISC-V is an open source instruction set architecture, and IBEX core is an open source 32-bit two-stage pipeline RISC-V CPU core. There are 71 registers in the IBEX core, which includes 2008 bits. So this is the overview of our proposed method. We use formal verification to find all candidate we use formal verification to perform backward tracing to find all candidate faults. For example, we specify fault-free effects such as no wrong results, no crash, no harm, and we use formal verification to find all faults that may violate our formal specifications. And with the help of formal verification, we can do exhaustive search in a reasonable time. Our method can be divided into 4 steps. The first step is to implement a fault injection mechanism. As shown in this picture, the fault injection mechanism we use is pretty simple. We implement an XOR gate before each register in the IBEX core. Inputs to the XOR gate are correct inputs to the register and a fault control signal. So one may ask, how do you prove the mechanism has no impact on the apex score when there is no fault. We develop strobe properties to prove this. So there are two apex cores, one golden and one with fault injection mechanism. We feed the same inputs and no faults to both cores. And we use formal verification to compare strobe signals from the two cores. Strobe signals are some key signals from the two cores, such as instructions executed each clock cycle and program counter and something like that. The second step is to develop formal properties in order to find faults according to effect of faults, such as silent data corruption, crash, hung, or nothing. We use strobe properties to find faults that may cause silent data corruption. We developed crash properties to find faults that may cause crash. And here is an example of our crash property. When a crash is encountered, the corresponding exception code is stored in a control status register. So by monitoring the value stored in this register, we can know the type of the crash encountered. And to find faults that may cause harm, there are three scenarios. The first scenario is that the core is waiting for an instruction. The second scenario, which is called dead state, means the core stucks in a specific state and it cannot leave this state. The third scenario, called live state, means the core stucks in a sequence of states and it cannot leave the sequence. We didn't model the last two scenarios as formal properties because liveness is involved. A liveness property means something good eventually happens, but you can't prove it ever happens. And we should be very careful with liveness in formal verification because we may use a lot of time and resource to prove a liveness property, but end up with nothing. So the third step is to abstract memories and to develop constraints. We are interested in bit flips in the registers inside the apex core. We are not interested in memories. So to reduce complexity and to speed up formal verification, we black box two memories. However, to make sure the apex core works correctly and works as expected, the constraints are developed. The constraints follow the handshake communication protocol between the apex core and the memories. Data from the data memory are arbitrary. However, instructions from the instruction memory are constrained to be legal, RISC-V, 32-bit, integer, multiplication, and compressed instructions, depending on the instruction address from the apex core. The final step is to run model checking and call of influence analysis. Model checking, which is a type of formal verification, is used to find faults which violate the formal properties. Call of influence analysis is used to find structural state faults. Call of influence analysis is also the basic theory used in model checking. So here is an example. Assume we have a finite state machine and we have two outputs there, out1 and out2. And we have a property saying out1 should never be 2. So to prove or to disprove this property, we need to construct a call of influence of the property. Inside the call of influence are all variables that may influence the value stored in out1. Outside the call of influence are all variables that cannot influence the value in out1. So after that, we can list all passes of variables inside the call of influence as shown here. And in pass 10, out1 is equal to 2. So this is a counterexample. So we find a counterexample of this property. So here are the results we got from our experiments. Inside the blue rectangular are different silent data corruption errors. Inside the orange rectangular are different crash errors. And the final one is the first scenario with for instruction of harm. So to make it easier to understand, I choose 3 examples from this table as shown here. And proven means all faults in a bit cannot cause a corresponding error. Bounded means a fault in a bit is less likely to cause a corresponding error. If there exists a counterexample, it is beyond the maximum time limit or trace limit. And in formal verification, bounded proof is acceptable because sometimes it is really hard to fully prove some properties due to various reasons, such as state explosion or time limit. And failure means a fault in a bit can cause a corresponding failure. And you can see in each type of error, the sum of proven, bounded, and failure is 2008 because there are 2008 bits in the apex core. And now we can know the vulnerability of each bit in the apex core, and we know all possible fault effects in each bit. So from the results, what can we learn? Well, obviously, some registers are more vulnerable than others. And faults in some registers can cause something. Faults in some registers can cause nothing. And we can use formal verification to find and classify faults according to effects of faults. And some bits are more vulnerable to certain errors. For example, faults in some bits can only cause silent data corruptions. In addition, even though in the same register, fault effects in different bits may be different. Yeah, so the final part, conclusion. Yeah, our method combines formal verification and fault injection. Our method can perform backward tracing to find faults according to fault effects. And our method can exactly search the whole state space and the fault list. And our method can successfully categorize single unit upsets. So in the future of our research, we will focus on using an alternative approach to find faults that may cause harm, because we want to avoid liveness in formal verification. And then we have shown that some bits are more vulnerable than others. So we can use different protection technologies with different costs and different efficiency to protect different vulnerable bits. And finally, we can use our proposed method to evaluate different protection technologies. Yeah, that's all. Thank you for listening. Do you have any questions?
Okay. Are there any questions for Bing from the audience? I'll just check on there. So there's one question online, Bing. So have you tried with methods that will detect those faults to show that the detection mechanism corresponds with the actual failures from those single fault injections?
So sorry, I didn't
don't
copy the last part.
So typically in a design, you want to be able to detect a fault when it happens. So have you looked into adding protection mechanisms and making sure that those protection mechanisms fire when the fault actually impacts the output? So the fault formal could possibly do a good job of that as well.
I think that's actually the last point on the last slide.
Okay, yeah, so
Yeah,
in the future research.
yeah,
Okay. That's
what
for the
we'll
future
do
research.
in the future. The last one.
Okay. So you can effectively show the equivalence between the fault detection. Okay, that would be interesting as well. Okay. Okay.
3 online.
That's 3 online. Sorry, there's another one. Let me. Yeah, Gina. Sorry. My mouse has gone dead. Bug. Yeah, how do you ensure that you've inserted the fault injection mechanism for all flops, for all the memory elements?
Firstly, we are not interested in memories. We are just interested in registers inside the Apex core. And,
Okay.
and you know, the one feature of formal verification is exactly search. So,
Right.
so yeah, and we implement a fault injection mechanism to inject faults to each bit inside the register inside the Apex core.
Okay.
So yeah, I think by combining this formal verification and fault injection, we can test all faults in the fault list in the Apex core.
Okay. Okay. No more questions? Okay. So we're now breaking for lunch. Thank you very much.